All right, so you asked for it, and now you got it. We had a lot of requests for a V6 Toyota video, and here it is. This is a 1GR FE engine, but the stuff I'm going to talk about probably will work for anything in the GR-FE family. There's a few variants. Some of them have just intake variable cam timing. Some of them have variable cam timing on the intake and exhaust. This engine finds itself in just about any Toyota in the 2000s, from the Frontier to various Lexuses to various Toyota models. So it's a pretty widely applied engine. And since a lot of you want to know how to build one, here we are. So this engine is being built for a turbocharged application, and it's an engine that's going to have a lot of torque, not necessarily very high revving, but pretty high boost, high torque, good low RPM power. A lot of this can be changed up with just a cam change and a different turbo selection, but this engine wasn't built to rev super high, just to withstand boost. So with that being said, let's get into it. The first thing about this engine is it has a really stout block. The bottom end is built really tough, amazingly tough. It has this bottom end cap. This is probably the toughest main cap I ever seen from the factory on anything, let alone a Toyota. So you have 4 main bolts and your cross bolt with 2 bolts here and here. I mean, this thing is stiff, rigid. It's made out of steel. This is going to withstand a lot of force, a lot of boost. Man, it's strong. I mean, the only thing that is maybe like that is maybe the LS engines. But, this thing can really take a lot of boost pressure. That's one of the sweet things about the motor, because once you surpass the amount of horsepower, nowadays with our technology, we kind of find that now we're surpassing the structural integrity of a lot of the blocks of engines we build, and this can take a lot. You can see the beefiness in the webs and all that. It's really strong, and we kind of dig that. Since this is going to be a boosted engine, this thing has a semi-closed deck conversion. Let me flip this over so you can see it. So now you can kind of see what's done to the block. So it had freestanding cylinders, so we did semi-closed deck conversion. They're Darden sleeves. They're a real close to interference fit. They're the mid sleeves, so they have this passage which allows the water to flow freely into the head and freely around the top of the bore. Now, some people say that that's important because this is the hottest part of the bore. Like this buttresses the cylinders pretty well. This is at the customer's request. Now, if it was up to me, I'd probably be using a top register sleeve. This means that the register is at the top of this cylinder, and there will be a CNC step. And then the sleeve will register totally on that. Like the Darden sleeve registers on the sides and then on the bottom, and then the cylinder head kind of holds it open. I prefer top register just because the block, the coefficient of aluminum is about twice that of steel. So a lot of times the block will be expanding more than the sleeve, and the sleeve will lose kind of its clamp, and then you lose your head gasket seal and blow a head gasket. And a lot of people will say, oh, the sleeve dropped, but a lot of times it's due to this. Now, Darden has a lot of experience, and they machine the sleeve with the top of it a little bit proud to kind of make up for this and to improve clamps around the cylinder. And it's also pretty tricky to machine this just right. So if you're going to use Darden, I really recommend you do what we did and then send your block to Darden and have them do all the machining. They're the experts. They know how to install their sleeve. So you're going to have a good outcome with Darden installing those sleeves. I don't know what could happen if you use your local machine shop. this is a lot of precision work and a lot of area and a lot of things that have to be really dead nuts for it to work. So send your block into Darden and it should be good. So the key to any good engine build for durability and good ring seal and power is really good machining. And this is where a lot of engine builds go south. Now we pay a lot of attention to machining and we control our tolerances very tightly. One of the tricks we use is to use a torque plate. Now, a torque plate is a thick, stiff metal plate that bolts to the top of the deck, and it simulates the distortion to the block that bolting a cylinder head will do. So you get the exact same hardware that you're going to bolt the head on, and you get the torque plate, you torque it down to the manufacturer spec, and then you bore and hone the cylinder. That way, the distortion of your cylinder is going to be the same as when the head's on there. Now, a lot of people say that's not necessary, but what we've measured is sometimes the cylinder walls can distort up to almost 2/1000ths of an inch. And with modern pistons, that's more than half of the piston to wall clearance that's getting out around. That also, when it's out around, it makes it a lot harder for the rings to achieve good seal. So regardless of what some people say, we think a torque plate's really important. And we use that on our engine builds. Some of the other things is we check all of our blocks to see if they need to be aligned honed. Some blocks, like a Subaru, they're not as substantial and they get out of whack, and almost every single one of them needs to be a line bored. An engine like this Toyota that's built like a brick shithouse, 95% of the time, you're not going to need to align bore it. Now, when you align bore it, is you shave a little bit of metal off the caps and you run a hone down the center of the main bores, and this keeps everything straight and parallel. That way you get good bearing wear. You don't get interference as the crank spins around, and less friction and stuff, and long life. When you take apart an engine that has correct machining, like the bearings all look evenly worn and everything, and when you see engine builders that have skipped this step, if the engine's been run hard, the bearings really look hammered and all over the place. But if you do a line bore, check to make everything straight and square, you won't have that. After doing all our machining or boring, we do a standard hone. Like we'll probably use anywhere from a 480 diamond hone to a 600. Usually it's something around the 480, especially with a turbo motor. And then we do a cork bonded plateau hone on top of that. So what that does is the 480 gives like scratches in the cylinder wall that act like an oil reservoir to lubricate the rings, even with a lot of cylinder pressure from boost. But the plateau honing gives this super nice smooth surface that you can probably see in here. This is low friction. It doesn't have the asperities that hook onto the rings and cause them to wear. So you get the best of both worlds. You get the oil reservoir from the coarser hone, but the smooth top finish from the plateau hone. We usually do variations of this on all our engines, and it depends if it's a naturally aspirated engine revving high or a turbo engine with a lot of boost. We might change the base hone grit some, but getting the proper cylinder wall finish is really important for your end use. After all the machining and all that, that's when we apply WPC. So the WPC is done last. You can see it in this thing. It's the smooth, like lustrous finish on the cylinder wall. But with good machining, everything lasts long. You don't have an oil burner. You have good ring seal, and everything is happy. So the Toyota has a really stout bottom end, and that extends to the crankshaft too. Now we're using the stock crank, but this stock crank can take a lot of power. I mean, the main journals are huge. There's a lot of overlap between the rod journals and the main journals, which really helps stiffness. Good counterweights. It's a forging. This is a really nice crank, and I mean, this thing could probably hold 1,000 horsepower, no problem. Some of the things we did is we chamfered the oil holes, balanced everything, and cryo-treated and WPC treated the crank. You can see the journals or have that kind of lustrous look, and that's the WPC. So that's improving fatigue strength and reducing friction. It's a really good unit. Probably not going to have any problems with that crank ever. For bearings, for main bearings, we're using ACL bearings. These are a tri-metal racing bearing. The tri-metal has a harder substrate and a kind of a thinner medium layer that kind of absorbs shock and provides some embeddability, and a very soft break-in layer on the top. That's the tri-metal. We're WPC treating the bearings. WPC treating usually increases the bearing's load capacity by about 20%, so that's a must if you have a non-coated bearing. The WPC will take off the coatings. So if you have a coated bearing, you probably don't want to do it, but anytime you have a non-coated bearing, especially if it's engine that's going to be run hard, I mean, it makes a big difference. So good application place for the process. We like ACL, Clevite, or King bearings. Kind of depends like what company has applications, but we use those three companies' bearings pretty much interchangeably. They're all good. They all hold up in racing engines, and they're all decent on the street. The rod bearings are also ACL, good stuff. For the rods, we're using Brian Crower rods. These are a pretty nice, strong rod. They're made out of 4340. That's high nickel and chromium steel. This alloy is particularly well suited for rods. It has really good impact strength and really good toughness. It's way stronger than what your stock rod is made out of. The bottom end has like a lot of beef around the bolts. That's a highly stressed part. The bolts themselves are ARP 2000, and they're about 180 psi yield strength, so they're really strong bolts. I think I calculated once, and they're close to 3 times stronger than the stock bolts. Small end has a silicon bronze bushing with a oil retention groove. Kind of keeps the pin lubricated. This is a really good piece. It's shot peened. The shot peening itself improves the fatigue strength about 100%. Fatigue strength isn't tensile strength, but fatigue strength is the number of times that a part can be cycled before it fails. So if you're pushing your engine hard and you're getting close to the yield point of the rod and the bolts, shot peening will improve the amount of cycles that it could take by about 100%. In addition, we also WPC treated the rod and the bolts and the small end bushing. WPC also improves fatigue strength. It really improves the fatigue strength of bolts. Bolts have threads cut in there, and the threads are all stress risers, which could lead to failure, but WPC kind of helps. It gets into the thread roots, and it makes it less likely of a place that a microcrack can propagate and cause failure. The WPC also gives lubricity in the bushing. Even though you have a oiler hole at the top and this groove that the hole feeds, you can still use all the lubrication on the small end, especially on a turbo engine that has a lot of pressure. Now, turbo engines, pistons are critical. So for pistons, we chose JE. Since this engine's not revving really high, but needs to withstand boost pressure, the construction is a lot beefier than we use on some of our naturally aspirated motors. And since it has a lot of rock, because of all the pressure on it, we were using full skirt pistons. A lot of our other like road racing motors and high revving motors, we use the strut type forging with like a like the thinner skirt surfaces for less friction. But in this high boost turbo motor, we have a full face here, so the maximum bearing area. We also move the number one ring land down, so the number one ring is supported better and it's less likely to bend. There's more material up here, so boost pressure and detonation pressure are less likely to bend the top of the piston and pinch the ring. So with turbo motors, you want your ring package down lower. OEMs put it up close to the top to reduce HC emissions, but since we don't care about that, we'd rather have our engine strong, we move everything down. We were not using any gas ports. Like, I kind of feel like on a high boost turbo motor, you don't need the gas ports to help your ring seal because you have a lot of gas pressure getting behind your ring anyway, so I didn't think they were necessary. So we're not running lateral gas ports, but we are running a pressure accumulation groove between the 1 and 2 compression rings. This kind of acts like a reservoir to keep the pressure on the second ring and help second ring sealing. It also kind of acts like a detonation trap that prevents any detonation pressure waves that might get past the first ring from upsetting the second ring. So pressure accumulation groove, and we're running standard oil ring. The ring set is kind of a cool ring set. I kind of like JE's standard ring set a lot. It uses a nitrided steel number one compression ring. They're thin, like 1.2 millimeters. So your top ring is nitrided steel. Your second ring is iron with a Napier profile. The Napier profile has like a hook on it on the face. It's really hard to see in video, but what that hook does is two things. It helps scrape the oil off the cylinder wall better. It actually gives like a more narrow surface, so there's less friction. It also gives a narrow surface that kind of breaks into the cylinder quickly. And it also is a narrow surface that helps seal compression better. So any blow-by that gets past the number one ring, the number two ring with the Napier profile is going to get. The oil rings are like low tension, narrow. They're light and won't flutter. They're pretty good at scraping oil off, and any oil that gets by them, the Napier number two ring will take care of. So even, if you're an old timer and you look how thin these rings are, you think there's no way that they're going to seal or be durable. But with modern technology, the rings are a lot lower friction, more durable, and they waste less power due to frictional loss. Another very interesting thing about this piston is these FE motors have what they call a tapered quench. So the quench areas of the cylinder head are aimed right at the spark plug. So you can see these quench pads on the piston. There's 4 of them. And you can kind of look. They're all tilted at an angle. And if you look at the combustion chamber on the cylinder head, you can see the matching flat quench things that are tilted. So what happens is the piston comes to TDC, all these dead areas of the combustion chamber, they get squished, and the squished jets are directed right at the plug. So all of these areas that are dead, that don't directly contribute to combustion, all that fuel-air mixture is actually being forced into the central part of the cylinder, right by the plug where it can ignite and take part in power production. So, you can kind of see that as this is coming and gets close, it squishes all this stuff out, and they call these squish pads. And all that squishing of this dead area into the center of the combustion chamber, that creates turbulence. So you get better mixing, better combustion, a cleaner burn, less likely to have detonation. All that stuff's cool in the turbo motor. It's good in any motor. So that's a unique thing about this engine. And like a lot of builders will just like machine it all and make a flat top or something, or not take advantage of the squish because they don't understand what it does. But we designed the piston top to exploit the squish. We also WPC treated the skirts and the ring grooves for lubricity and hardness. And we have JE's top ceramic coating. So this is an option you can order from JE. So it's a thermal barrier coating. It keeps heat out of the piston. Aluminum starts to really lose strength after 350 degrees. So if you can keep the heat out, your piston is stronger. One of the most important things about a turbo piston is the material. Now these JE pistons are made out of 2618. That's a low silicone alloy, particularly well suited for turbocharging any kind of forced induction or nitrous. 2618 is a lot more ductile than other common piston alloys. It's a lot more ductile than hypertectic cast pistons like typical stock pistons. And it's also a lot more ductile than 4032 high silicone, which is used for some forgings. In the past, the drawback to 2618 has been it expands more with heat and it rattles a lot more, even sounding like a diesel sometimes because you have to run a wider piston to wall clearance. But JE has a lot of different cam designs, and with their FEA and thermal analysis, they have a lot better idea of how the piston's going to expand with heat. Like, of course, it's going to expand a lot more on the crown side, a lot more on the exhaust valve side. So what they do is alter the skirt profile, or what they call the cam of the piston. So where the piston's going to get hotter and expand more, they have it more clearance, and then where it needs to be tight, like in the skirts, they have less. This way, the piston could be pretty tight in the bore and not risk seizing. This is all some of JE's engineering. So modern pistons, 2618, particularly JE's, are actually amazingly quiet. When we were kids, these things used to be like diesels. They used to like rattle around, burn a lot of oil, and the rings and everything, and the cylinder walls would wear really quickly. But it was considered to be the price you had to pay for the toughness. Well, now you don't have so much of that, and I've used 2618 on daily drivers, and it comes out fine. Maybe some of the disadvantages of 2618 is you don't have the hard carbide inclusions like you do in hypertectic alloys, so they wear out a little quicker than stock pistons. Now, I've always said that there's a lot of difference between long wearing and strong. These are strong. Your stock hypertectics are long wearing. That's why some of your Toyota engines can last 500,000 miles. They can last 500,000 miles, but they're not going to put up with the boost. Now, these will put up with the boost, and maybe you'll get 100,000 out of them, but that's still pretty good for a highly modified engine. This being a turbo motor, we specified a thick wall, stiffer piston pin. On the high revving, naturally aspirated, lightweight's always important, but for a turbo motor, high boost, stiffness of the pin is important. One of the main reasons why you want a thicker, stiffer pin is that the thin pin tends to flex and grab in the small end of the rod. And what it'll do is it'll spin the bushing right out of the rod, and then you'll have play in your small end, it'll bang around, and eventually the rod and the pin will fail, catastrophic engine failure. So stiff pin with boost, very important. So now onto the cylinder head. There's not a lot of camshafts available for these engines, but for a turbocharger, you don't really need to worry about cams too much, especially if you're building it for quick response, torque, and bottom end. So we're using the stock cams. The cams have some interesting features, like Toyota does some cool things to help their durability. Um, they use like a chill when they cast the cam, and the chill is like a heat sink that sucks the heat out. So it as the metal like cools down, it actually gets harder. So you can kind of see the lobes kind of look different on the flanks and at the tip. That's because it's chill cast, and the lobe part's actually a lot harder. So you have the cam itself, it's pretty malleable and not likely to crack, but the lobes are hard, and they're not going to wear out too quick. Kind of like a samurai sword. We also WPC treated these for long life and good wear and low friction. For the valve train, we used all SuperTech stuff. So we have a SuperTech intake and a SuperTech exhaust valve. The intake is black nitride stainless steel, and it has like a flat contour, kind of like a nail head. And so when the fuel air mixture is coming into the port, a flat contour works better, especially at lower lifts. It helps turn the air into the combustion chamber smoother and less turbulence, and it improves your flow. The valves also have a reduced stem, and believe it or not, that helps port flow maybe on some motors like up to 15%. I didn't flow bench the difference, so I don't know exactly what it does on this Toyota, but it's a little free thing that gives you more flow. And the valves also above the 45 seating surface have a 30-degree back cut, like atop of the 45, and that also helps low lift flow. That kind of like makes like a smooth venturi from the valve seat to really help the air get in there. Now, low lift flow is probably the most important thing when doing heads and headwork and consideration, because your valve actually spends more time opening and closing than it does at maximum lift. So of course it's good to have flow all throughout the lift curve, but in low lift you have two chances to get the stuff in and out, and there's more dwell time there. So it's good to do all these little details to help your low lift flow. That's like free power. Now our exhaust valve is Inconel. Inconel is a like heat resistant alloy that can take high temperatures, exactly what you need in the exhaust valve. It also has this reduced diameter stem to help flow. But if you notice, the exhaust valve has more of a tulip shape to it. So when the intake valve is flat, the exhaust valve is more tuliped. And what this does is the tulip shape helps flow, and flow is going the other way, like out of the combustion chamber into the exhaust port. So you can kind of see it here, like a flat nail head on the intake and a tulip on the exhaust. Like the intake, there's also a 30-degree back cut on top of the 45. What we like about SuperTechs is they're all forged as one piece. A lot of performance valves, even like famous name ones, the stem is spun welded onto the head. That's a fine procedure and it works pretty well, but my feeling is that a one-piece forging is stronger and safer and less likely to come apart if bad things happen in the engine. Like if you tag a piston, it's less likely to crack the valve head off. It might bend it, and some things will get messed up, but hopefully your engine won't get totaled. Good valves and at a really reasonable price. Now, turbo engines with a lot of boost pressure in the intake port, they tend to blow the valves open, especially with modern engines that have really low tension valve springs. So a lot of times they need some help by upping the valve spring tension. That's because the boost pressure is working against the springs. So we used SuperTech dual valve springs. There's an inner spring and an outer spring. the fit's pretty tight, and the reason why the inner spring on the good quality race spring is tight is that friction kind of acts like a damper and helps reduce spring surge. So your better springs have a really tight fit there. We WPC treated them. Valve springs are a really highly stressed part, and breaking valve springs in the race motor is not unheard of. It's a fairly common problem. We found by WPC treating the springs is they run cooler and they last at least twice as long before they lose their tension or break. Believe it or not, valve springs actually run pretty hot. So if you're running at like 7,000 RPM, and even if you're getting into the 8s or higher, it's not uncommon for the springs to reach 350, 400 degrees or more. Some engines that run at high RPM for really long periods of time, like NASCAR engines, actually have oil jets pointed at the springs to keep them cool. Like any metal, the hotter they get, the more they fatigue and the less long they last. So having your springs get hot is not good. And we found that WPC treating the springs actually has them run a lot cooler. Like, I don't know exactly how much cooler, but I have noticed that some of our high RPM engines, you could tell the springs are hot. Like, they're all discolored and everything. But when we've WPC treated the springs, I haven't seen any WPC treated spring that has that heat discoloration on it. So it's got to be running a lot cooler. Now we're running this lower spring seat from SuperTech that keeps the lower spring perfectly centered, and we're also running a SuperTech titanium retainer. Now on race engines, I've actually seen the hole here for the keepers get worn out and kind of wallered out. It's because the springs rotate as the engine's operating, and the retainer rotates too, so the keepers actually wear into the retainer, especially titanium ones, because steel doesn't necessarily wear too well on titanium. Now, titanium's a lot better than like some of those aluminum retainers, but it wears faster than steel, and when you WPC treat them, the wear rate really drops to where maybe it even wears better than an untreated steel part. As far as like keepers, we run SuperTech forged machine keepers. They're really strong. They're hardened. Keepers are critical to prevent your valves from dropping. Now, the part number we use is the same as the Honda K-Motor and K20, K24. It also works on the SuperTech Toyota parts. So if you're using that, that's the way to go. So for the cylinder heads, we talked about Toyota's innovative tapered squish zones that we really like. These heads, we did some hand porting, so it's fully hand ported. You know, what we tried to do is keep the overall volume of the ports low, so we have our high port velocity. But we did the usual tricks of blending the valve seat into the bowl and the bowl into the port and cleaning up the short side radius. And this is where you get most of your flow improvements. And we also opened up and knocked the port splitter back. That's where flow usually chokes down a lot. So these guys should flow pretty well. We're using SuperTech bronze valve guides that wear better. So we cut the seats with our new CNC valve cutting machine. This makes a smooth radius from the combustion chamber to the 45 and into the port. So it's a nice, smooth flow transition, really helps low lift flow. I mean, we've seen up to 50 horsepower gain over like a just regular 3-angle valve job from a Surdy machine, which is a good machine in itself. So the new one's the way to go. It's free horsepower. And of course, we've done the normal tricks like surfacing and all that, but it's nice turbo porting. It's small, high velocity. It's not going to make the engine laggy or anything, and it should pick up really well. There's some other things like small details that we do on our engines that maybe other people don't. Like if you look at the block and some of the heads, all the oil galleys, we removed the freeze plugs. We found that sometimes on these engines they fall out and you lose oil pressure. So we tapped them and we're using screw-in plugs, so there's no way they're going to fall out. You should also usually remove those things whenever you do a motor, because on this particular motor, there's a lot of sludge behind the OEM plugs. So it's in the main galley plug in the front and the rear of the block, and the oil galley plugs in the heads. We did this. And there's also an oil galley plug in the cam. So after all that and the WPC treating, everything was ultrasonically cleaned to make super clean, and now it's all ready to assemble. So if you have a Toyota GR FE family engine, these are some of the things we can do to get you more power and more durability. I know a lot of you Tacoma guys want more power, so here's the basis of it. If you like this content, be sure and subscribe to our videos. You can go to motoiq.com and read thousands of tech articles. No matter what kind of car you own, there's probably something that we did in there that will interest you. If you want us to build your motor or do work on your car or truck, you can go to motoiq.com, click on the garage service link, and fill out the form, and we'll be getting back to you. I hope you found this interesting. We had a ton of requests on this motor, so I hope you like it. This is for a particular type of application, but we can build a motor that's tailored around whatever you're going to do for it. So until next time, I hope you enjoyed this video.